If you ever wanted to know the impact of solution annealing to the final product quality in pharmaceutical engineering, stay tuned. Hi, my name is Thorsten Köcher. In one of our last videos, I was talking about delta ferrite. In this video, I would like to talk more about the fact or the method to minimize, to reduce delta ferrite, as we have received a lot of questions from you on that. And I would like to do that with regard to the manufacturing of such part here. This is a manifold with high requirements on tolerance and corrosion resistance. So when you do such a part, you certainly do a welding operation. And this welding operation is certainly an impact on the metallic structure of such a system. Usually such manifolds are being made in either 316L or 904L. And with regard to both alloys, we are figuring specific undesired intermetallic compositions that have a negative impact on the one hand with regard to corrosion resistance, on the other hand with regard to mechanical stability. Whereas 316L, we're talking about delta ferrite, and that is causing a lack of corrosion resistance. With regard to 904L, we are talking about He phases, Lavis phases, or Sigma phases. And those are causing a lack of mechanical stability. Because it's easier, I would like to draw your attention more to the 316L phase diagram here and explain this a little bit in detail. When you have the molten mass, you see that with regard to 316L, we have a composition of roughly 18% chromium and 10% nickel. When you lower the temperature, you will at some point reach a two-phase area in this diagram. And in the two-phase area, you create on the one hand chromium-rich crystals, and the remaining molten mass will decrease with regard to chromium. At some point, when you reach the eutecticum, you will see that more and more different crystallization takes place, and you have a real mix of different ferritic and austenitic structures and crystals in there. At some point, you can see that the austenitic structure is the only structure that is actually thermodynamic stable. So why do we figure a problem anyway? We figure a problem because during welding, this transition, this section will be passed in just some tenths of a second. So the temperature transition from 1500 degree to 1300, 1200 degree will be done in some tenths of a second only. Yeah? And therefore, those ferritic crystals, they cannot dissolve and transfer to the austenitic structure anymore. So you need to help the material. You need to do something to move the atoms, but remain the mechanical stability of your system. And this is what you do with regard to solution annealing. During solution annealing, you elevate the temperature roughly up to 1040 C, which is low enough to remain the mechanical stability, but high enough to promote, or let's say to help the atoms to move, and that the ferritic crystals will be dissolved in the austenitic crystals or in the austenitic structure. This is what is done during solution annealing. Certainly you need to take care about the surrounding atmosphere around the part, because you want to avoid any corrosion of the part due to oxygen. That's why you either need to do it under protective gas or under vacuum. We usually do our solution annealing processes under vacuum, and That's why everything is staying like this, nice and shiny. Well, I hope I could describe the actions which are necessary to do solution annealing and to keep a high level of hygienic design and mechanical accuracy. And if you have further questions, we are certainly open to those and would be very happy if you would subscribe to our YouTube channels and if we could welcome you in one of our next videos. Thanks so much.